how do we find the unknown unknowns? Because this is the really big question for astrophysics. What is the thing that we're going to find in our new data that we didn't expect to see?
We have Professor Anna Scaife here to give us the opening talk. She's a Professor of Radio Astronomy at the University of Manchester. She's in fact one of the first 5 AI Fellows at the Alan Turing Institute. She's also Director of Research at the Centre for Doctoral Training and Decision Making for Complex Systems. She's Deputy Editor-in-Chief for the Royal Astronomical Society's Techniques and Instrumentation Journal. She's also Subject Editor for the Royal Society Open Science Journal. She's won a number of outstanding prizes, one of the top 30 young researchers, and also awards from the Royal Astronomical Society. So too many to go into in detail, but she's going to talk to us about foundation models in astronomy. So over to you, Anna.
Thanks, Jason, and thank you very much for the invitation to speak today. It's a pleasure to be here. I'm going to talk about AI and astrophysics, and specifically I'm going to talk about 2 key aspects of that, and those are foundation models and discovery. So to sort of get straight into it, I want to start by defining what a foundation model is, because I think there's some degree of confusion about this still. So a foundation model is a model that can be used for multiple purposes. So basically, instead of training individual models for different purposes, you train one big model once, and then you reuse it for many different downstream problems. So it's more of an efficiency, but it also provides a context for those downstream problems. People tend to think of LLMs as being foundation models, and they are, but they are only one example of a foundation model. You can train a foundation model on any kind of data modality. Typically, they're trained on very large data sets, and how they're trained is not a property of the foundation model. They could be a supervised model, an unsupervised model. They could be trained in a hybrid fashion, but their purpose is to learn the underlying semantic structure of the data that they're trained on to create that latent representation of the information that's in those data. And from that underlying structure, that should make them adaptable to many different tasks, either directly or via a process known as fine-tuning, where you take your representation and you tweak it a bit based on some new information. And with that, you can then use them for lots of different purposes. So I'm going to talk specifically about foundation models in astronomy. Astronomy is a science that is heavily data intensive. We're very rapidly entering the exascale regime in astrophysics and astronomy these days. And so foundation models and AI are becoming quite an integral part of our scientific process, because there is simply no way to interrogate our data in a manual or by eye way anymore. Foundation models are also starting to grow, and these foundation models in astronomy tend to be grouped by the modality of the data, because in astronomy we're not primarily talking about text or video or images. Images are definitely in there, but we're also talking about frequency spectra, we're talking about polarization data, we're talking about time domain data. We have many, many different modalities of data. And so we tend to build foundational representations around those different types of data and across those modalities of data, so joint modality models. Now, this is a cutout from a much longer list of foundation models in astrophysics that was very helpfully put together by a guy called John Wu, who's at Space Telescope in Baltimore. Now, I'm not going to talk about all of these foundation models today. There's simply not time. I'm going to talk about these 2 specifically, which I'm sure that you can't read at the back. But the 2 I'm going to talk about are the ones that have come out of my research group, which are the ZooBot model and the Radio Galaxy Zoo model. And the reason that I'm going to talk about these is not only because they're the ones that I know the best and can tell you all the nitty-gritty details about, but because, as far as I'm aware, the ZooBot model is currently the most widely used foundation model in astrophysics today. And moreover, it's the only one that has been fully operationalized within an observatory. And I'll show you how that's been done a bit further into the talk. So the ZooBot model is a foundation model for galaxy morphology, and it's built on data from a project called the Galaxy Zoo. Can I ask the audience if anyone has heard of Galaxy Zoo? Oh yes, lovely. Anyone answered some questions in Galaxy Zoo? Yes, thank you very much. Your data was used to build the ZooBot model. And you are acknowledged in the ZooBot papers, so thank you once again. The Galaxy Zoo project, for those who don't know about it, was a citizen science project to which more than 1 million individuals have now contributed, asking citizen scientists questions about the morphology of different galaxies, because the morphology of galaxies is intrinsically tied to the scientific analyses that we do in astrophysics. So what do those galaxies look like? Here's a little sort of montage, or zoo, of galaxies, if you like. These are real galaxies, and hopefully everyone can recognize that sort of that iconic spiral structure that we associate primarily with our own Milky Way galaxy, where we live. And you can see that these galaxies, they're all recognizable as galaxies, but they are all different, right? Galaxies are a bit like faces. You can look at them and you can say that's a galaxy, but every one is individual. And so understanding the morphology of galaxies is a lot like understanding facial expressions, except we use it in a very different way. The colors are also representative of the physics in the galaxies. Young galaxies tend to be blue, they have active star formation. Older galaxies tend to be red, we call them red and dead. So what you're seeing here is not only different evolution in the morphology, but different evolution in the colors of the galaxy. And all of this information goes into the analyses that we do in astrophysics. So one of the beautiful things about the Galaxy Zoo project was that it provided this huge data set, not only for astronomers to use directly. There have been many discoveries directly from the answers provided by citizen scientists in the Galaxy Zoo project, but it also allowed us to build a foundational AI representation for galaxy morphology. And the way we do that is quite simple. We take the corpus of citizen scientists' answers about questions, and we build a model to predict the distribution of responses to all of the questions. So the model predicts the answers to about 200 different individual questions or tasks within the Galaxy Zoo online system. The original model was built and trained on about 300,000 galaxies using 10 million responses from citizen scientists. In the more recent versions of the model, we have about 1 million galaxies in there. So how does it work? How does the foundation model work? So the basic principle is that we take that data set, which is a large data set, we train this in a multitask supervised sense to provide that latent foundational representation that gives us that structure of the information in the data. And once we have that trained model, we can then show it a new galaxy, our test sample, that wasn't in our original data set. We can put it through the model, and depending on where it ends up, see if this works. So for example, here, that gives us the answers to all of these 200 questions immediately. Now, what I'm showing you here on the right is a representation of this latent representation. Now, the AI model itself learns quite a high-dimensional latent representation. What I'm showing you here is a sort of flattened version of this. So for those who understand the technicalities behind this, this is done using PCA and UMAP to provide a two-dimensional representation of the ZooBot pre-trained representation. And what you can see is that the morphologies sort of have different clusters around the representation. We've got our edge-on galaxies over here. We've got our elliptical galaxies over here. They look like blobs. We've got our spiral galaxies down here. And so when we encode this spiral galaxy through the trained model, it'll end up somewhere down here in our latent representation. And so when we take a new survey of the sky and observe 1 million galaxies, we can instantly put them through this model and answer all of the citizen scientists' questions from Galaxy Zoo. Now, the model was trained on 300,000 galaxies. Obviously, there weren't 300,000 in that compressed representation. If we look at the distribution of those 300,000 galaxies, it looks like this. So the general overall shape is the same, but now every dot I'm showing you is a galaxy encoded through the model. And the reason I'm showing you this is to highlight these red points in the middle, because these red points reveal something about the model that we didn't expect. These red points are points where the citizen scientists have not answered a direct question about the galaxy, but where they've used a free text box on the Galaxy Zoo interface to make a comment about a galaxy. Now, that free text information isn't used in training the model, but we can use it to color code the data points afterwards. And these are the data points where the citizen scientists said, this is a weird galaxy. So these are the odd galaxies. And even though we didn't actually train the model to find these galaxies, here I'm just showing you the correspondence between the two images, the model has grouped them together. Now, it doesn't matter that they're not in a tight cluster. That's not important. The thing that's very key for us here is that they are in a space that is navigable. We can actually map between these galaxies and then explore around them to find more examples of these odd galaxies in order to find out why they're odd. And that's exactly what we did. Now, just as a slight aside to that, if you design a model specifically to look for odd galaxies, it doesn't do the same thing. So this is a kind of model designed to look for odd galaxies. It's called an isolation forest. It's designed to isolate strange examples of whatever kind of data you're showing it. When you design a model to look for strange things, it puts those strange things at the edge of the representation. Now, this is absolutely fine. It can help you find them. The problem with it is that it's very difficult to navigate around the edge of a representation. And so having this kind of cluster makes finding more of these examples easier. And it allowed us to determine that there were three types of galaxy that were being called weird by the citizen scientists. They were either examples of merging galaxies that I'm showing you over here, a type of galaxy that is technically known as an irregular galaxy, or more interestingly, ones like these ones in the middle, and these are called ring galaxies. Now, ring galaxies are star-forming galaxies, like our own Milky Way, but instead of having a spiral structure, they have just a circle or a ring of star formation around a central nucleus. And historically, they were thought to be very rare and potentially not very interesting. However, once you know that the odd galaxies have a lot of these ring galaxies, you can pull out a small validation sample, just 10 examples, and you can go looking for more of them. And so that's exactly what we did. We put together a small validation sample. So our full validation sample was quite large, but with even a small validation sample of about 10 galaxies, you can fine-tune the pre-trained Galaxy Zoo representation to look specifically for ring galaxies. And with only 10 known examples, you can get back about 85% accuracy on finding those particular types of galaxies. Now, the number of lines on here are showing you the difference between how good the model is at finding ring galaxies, depending on what that initial training was done on, whether it was done on the full Galaxy Zoo dataset, that's GZ multi, or whether it was done on a subset, that's the GZ smooth, that's the purple line, or whether it's done on something non-astronomical like ImageNet, and that's the red line. I'm going to come back to this point later on again, which is that you can see that with the ImageNet line, you can eventually get to the same kind of performance as training on the Galaxy images, but you need a lot more examples for your fine-tuning. In fact, you need 10,000 rather than tens. The grey line here is if you just built a supervised model to look for ring galaxies and just trained it from scratch. And you can see that you don't really get any performance until you get to about 10,000 galaxies. So we fine-tuned the ZooBot model to find more of these ring galaxies, and that's exactly what we did. We found a lot more. In fact, we found 40,000 more rare ring galaxies. So this particular type of galaxy, which we thought was, very sparse in the universe, turns out to actually be way more normal than we previously thought. And more interestingly, they also sit in a very specific part of galaxy evolution called the Green Valley, which is between the blue young galaxies and the red old galaxies. And that's important because the statistics of how many galaxies sit in different parts of evolution tell us about the evolution of the galaxies. So this is quite a key thing for understanding galaxy evolution more generally. And of course, the press like to pick up on the AI and describe this as cyborg astronomy. But finding rare ring galaxies or lensed galaxies is not the only thing you can do with ZooBot. As I said at the beginning, the ZooBot model has been used for a whole range of downstream science now, whether that's directly used or fine-tuned for specific tasks. There are about 250 scientific papers that have been based now on the 2 original ZooBot papers, and they cover all different types of galaxy evolution science. And I'm just showing you a range of some of the examples that have come out of ZooBot. I'm not going to go into these in detail. I'm going to talk more about the model itself and the AI, but just to give you an idea of how these models are being used. The other exciting thing that's been done with ZooBot is that it's been operationalized within an observatory. And the observatory that's operationalized it is the Euclid satellite launched by ESA. So this is Euclid. Euclid is designed to make surveys of about 1/3 of the full sky. And in doing so, it's going to detect a couple of billion galaxies. And of those billions of galaxies, about 100 million are likely to have morphological structure that we can analyze for astrophysical science. The key scientific objective of the Euclid satellite is to understand the nature of dark energy. But it's also looking for things like deviations from our theory of general relativity. And those are the kinds of things that you can do with these large surveys that return big populations of astrophysical objects. So ZooBot was operationalized within the pipelines for Euclid, which meant that when Euclid made its first quick release data set, so this is like the early science out of Euclid, this came out last year, the ZooBot model was able to classify the galaxies from that quick release data set. These are some of the groups that it classified them into. That data set was about 400,000 galaxies, which is a fraction of the 100 million that will be taken out of the full data set once 1/3 of the sky is covered. But the key thing about this is that a morphological catalogue like this from Euclid would normally take about 2 years to produce from a satellite mission, whereas ZooBot was able to produce it immediately with the data release. And so the AI accelerated the science here enormously, and people are already doing downstream science with these data. Now, where do we go from here? Well, one of the questions that I often get asked is, why do you pre-train on the Galaxy Zoo data? Why don't you just pre-train on larger data sets like ImageNet or the standardized benchmark CS data sets? Don't they have the same underlying morphological information in them? And the answer is that yes, you can do that, but what our results have shown is that for whatever downstream task we throw at our foundational representations, so here's our ring galaxy fine-tuning task, here are 4 other astronomical downstream tasks, we find that the performance is improved by using in-domain data for our pre-training. So we do think that this is important, and that was also shown in those performance curves that I put up earlier for our ring galaxies. So how you pre-train your foundational model is important. But it does mean that if you want to use in-domain data, then a supervised model is going to have limitations. And ZooBot, just to remind you, is a supervised model. It's trained against citizen scientists' answers to the Galaxy Zoo project. So we looked at how far we can go with this. How far can we scale this model? Because, that's where you get performance from scaling your models up. And here I'm showing you the performance of the model in terms of the loss, so smaller is better, as a function of the data set size. And this scaling analysis was done using almost 1 million labeled galaxies, which is, as far as I know, the largest labeled data set in astrophysics. This figure over here is showing you the number of labeled galaxies for different galaxy morphology works in the literature, that's all the blue crosses, against the number of parameters in the models those works used. Now, there are two things that came out of this scaling analysis. The first thing is that we don't have enough data to do these supervised models at larger scales. The models all saturated about 100 to 150 million parameters, which is nothing in terms of giant models. So supervised learning is only going to take us so far in astrophysics. Astrophysics is a science that's entirely based on inference. We can't create data with a specific label. We have to use human labeling. And so labeled data is a problem for us. We live in this weird dichotomy where we have too much data and yet not enough data. The other thing we also showed is that all of these models in the literature are over-parameterized for the amount of data that they're trained on. So we need a different paradigm, and I'm sure the experts in the audience will know where I'm going with this. Because if you don't have labels, then you go to self-supervised learning. And that's exactly where we went with ZooBot. The current generation of ZooBot is a hybrid supervised contrastive model. Because we have some labels for Galaxy Zoo. However, for other branches of astrophysics, like, for example, radio astronomy, which is primarily where I do my science, we don't have any labels, or we have very, very few labels, sort of hundreds to thousands of labels, which are, no good at all for building supervised foundational representations. So in fields like radio astronomy, we really need to go to self-supervised learning immediately. Now, I realize that radio astronomy is perhaps a bit more of an obtuse concept for people than optical astronomy. I think everyone can look at a spiral galaxy and say, yes, that's a galaxy. However, perhaps not everyone can look at a radio galaxy and say, oh, yes, that's a radio galaxy. So I just want to illustrate what I mean by a radio galaxy. So here is an optical image of the sky, and I'd like to highlight this guy in the middle. So this is a giant elliptical galaxy. Slightly weird shape. Maybe it's interesting in the optical. However, it's far more interesting in the radio, because if we look at the radio emission for this galaxy, it looks like this. Now, these images are on the same scale, and what you're seeing in the radio is not the star formation or the gas in the galaxy. This very compact object that you're seeing is the supermassive black hole at the center of the galaxy. And through conservation of angular momentum, the material that is accreting onto that supermassive black hole is being ejected as ultra-relativistic jets of plasma into the surrounding environment. And that's what you can see on either side here. And as those jets hit their surrounding medium, they impact and cause shocks, and the material flows back around the jet. So this is a radio galaxy. In my opinion, it's far more interesting than an optical galaxy. And when you look at the radio sky, you see a lot of these. So this is a deep field image, an early deep field image from the Meerkat telescope in South Africa, operated by the South African Radio Astronomy Observatory. It's a precursor instrument to the Square Kilometre Array, which is headquartered here in the UK. This is, in fact, a photograph of the telescope, superimposed on one of the images from the telescope. This is an image of the radio sky, and to summarize it, basically every bright point that you're seeing in this image is a supermassive black hole. And if you zoom in on them, you can already see that some of the closer ones have this jet structure that we would expect. Here are some little zoomed-in radio galaxies. These ones are beautiful ones where we have very high-resolution images. In general, the multitude of galaxies that we see will be at lower resolution, and we have to do a lot more work to really analyze the physics that's going on. So to build a foundational representation from radio data, which is what we did, we used a fully self-supervised model that just looked at the structure of the similarity for the radio galaxies. Now, you can do all kinds of downstream science with this kind of model, just as you do with the Galaxy Zoo model, which I'm not going to talk about in detail, but I wanted to talk about how we make discoveries in those data. So in the same way that we can go looking for rings in the ZooBot model, we can also go looking for rare objects in the radio foundation model. So one example of that might be to go looking for something like this. Now, there's a reason why radio astronomy is often referred to as blobology, and that's because typically we work with images that look a bit like this. This is a rare type of radio galaxy called a hybrid Phaneroff-Reilly galaxy. For our particular foundational representation, it's not in the training data. We would consider it probably out of distribution for the fine-tuning that was applied to the model. But if we encode one example of this type of galaxy through our model, we can then go out and find a larger sample of these rare hybrid galaxies. Now, these are actually really, really difficult to find, even by eye, simply because the morphology is very difficult to distinguish from other types of radio galaxy. However, we do know what they look like. We know that they exist. So this is what I would refer to as a known unknown in our data. In terms of our discovery space, we know what we're looking for and we can go and find more of it. But then the question is, how do we find the unknown unknowns? Because this is the really big question for astrophysics. What is the thing that we're going to find in our new data that we didn't expect to see? Where is the semantic shift in our data? And so doing that is a different kettle of fish. We need our model to identify something when we don't know what it is. So we need to ask our model, what is the weirdest thing in this data set? What is the most unusual thing in this data set? So there are different ways of doing this. One approach that we've been pursuing recently is to look at mapping the outputs of our foundation models onto what's called an energy function to create probabilistic distributions for our in-distribution data and our out-of-distribution data. So this was a method that was introduced into the literature in about 2020, more generally into the CS literature. We've adapted it to work with our Bayesian models because our foundation models have Bayesian front ends. And we've been applying it to the radio survey data to find what are the strangest objects in these radio data. And I say strangest, I'm going to say least in distribution quite a lot, because out of distribution is quite a difficult thing to specify in astrophysics. Astrophysics is much more of a spectrum than discrete buckets, if you like. For example, if I take the pre-trained foundation of our radio galaxy model, it's trained on these kinds of data which were taken from the VLA telescope in the US, and they contain two types of radio galaxy. Now, I could make observations of those same kinds of radio galaxies using the Meerkat telescope in South Africa, and they would look like this. Now, these data have different properties, but it's the same underlying astrophysical system. So it is shifted. Is it out of distribution? Kind of, but also kind of not. However, if I show the model some optical galaxies, like the ones from the ZooBot model, those are definitely out of distribution. It's different astrophysics and it's different data. So there are gradations of being out of distribution or being less in distribution in astrophysics. And we found that, subject to some caveats, which I'm happy to talk about if anyone's interested, these energy score models with our Bayesian front end actually work to separate these distributions very nicely. These are real data from our model separating these three types of data set. And we've been able to use this to map the degree of weirdness or the degree of not in distributionness across the radio galaxy latent representation. So this is the latent representation for our radio galaxy model, and it's color-coded by how in distribution it is or how not in distribution it is. And the very in distribution points, which are blue, they look like this, right? They're our typical blobs for our radio galaxies. And you can see that the out-of-distribution ones are clustered around the edge, just like the isolation forest clustered the ZooBot out-of-distribution points right back at the beginning of the talk. What we can do with this is that we can find the single most odd galaxy in the data set, and that's this one, which just looks a bit waffly, but what that's telling us astrophysically is that the environment around this galaxy is very strange. And in fact, this kind of galaxy is extremely interesting because it's thought to be a precursor for something that's called a radio ghost or a radio halo that we find in clusters of galaxies. And so identifying these kinds of galaxies is very important. Now, this is not a new discovery because this was in our data set, and everything in our data set was known to be a radio galaxy a priori. So this is not semantically new. This is just the weirdest radio galaxy in our data set. But if we want to be able to find something new from new data, which is the next stage, we need to be able to find where those points are. And this is the approach that we're planning to take. However, I want to end on a slight caveat to that. We are a little bit worried about how well the foundational representation will understand those strange objects. We've been looking at the characteristics of all of our data in terms of the intrinsic dimension of the signal. Now, intrinsic dimension is a concept from manifold theory. It basically tells you the smallest dimensionality that a piece of information can have and still be fully represented. So if something is fully represented, you would expect its intrinsic dimension measured in the data space, i.e. the images that go into the model, and the latent space, the information that comes out of the model, to be the same, because those are just two ambient representations of the same data. And that's what we see for our in-distribution data. The data space or images that go into our model have basically the same intrinsic dimension as their latent representation, which is given by this line. However, as the galaxies become weirder or less in distribution, their intrinsic dimension increases in data space, but decreases in latent space. So the representation is actually not only not fully capturing this information, it's losing information about these objects. And so how we then modify our model to actually ensure that the potential for discovery is not lost is the next stage in what we're doing. So I will finish there. Thank you very much for listening. I wanted to just summarize the advantages and disadvantages that I see for foundation models. I do think that foundation models are the way we are going in astrophysics. They are the single most effective way of actually learning the underlying structure of our large databases, which are really large, and allowing us to query those in a meaningful way. And as I've shown you, they can reveal untrained relationships in those data sets, which is also extremely useful. The disadvantages are that the science we want to do with those pre-trained representations needs to propagate uncertainty into the final analyses. And so until we can actually provide well-calibrated uncertainty estimates and understand the biases that are being imposed by those foundational representations, then we need to be a bit careful about how that science is undertaken. So I think the future outlook for us is that I genuinely think that astronomy archives will be transitioning into queryable foundational representations. I think that they will be, in most cases, inherently multimodal to underpin the survey science. But a key element that we still need to overcome is to quantify the selection biases, or the biases that those foundational representations introduce into our analyses, in the same way that we very carefully quantify and mitigate our instrumental selection biases. Thank you very much.